In this video, we're going to wrap up section 6.4 and use the sine and cosine functions to model real-life data. Sine and cosine functions can be used to model many real-life situations, including electrical currents, musical tones, radio waves, tides, and weather patterns. So here in example 7, we're going to find a trig model to fit some data. Throughout the day, the depth of water at the end of a dock in Bar Harbor, Maine varies with the tides. The table shows the depths in feet at various times during the morning, and this is real data that comes from Nautical Software Incorporated. First, we're going to use a trig function to model the data that we've plotted the points for. And then we're going to use that data to find the depths at 9 a.m. and 3 p.m. And in part C, we're going to talk about a scenario here. A boat needs at least 10 feet of water to moor at the dock, from which times in the afternoon can a boat safely dock. And we're just going to talk about that and look at the function graphed on a graphing calculator. So here's our data. The times are on the left, starting at midnight to noon, and the depth is our y value given in feet. First, let's look what this data would look like if we graphed it. So at midnight, we were at 3.4, so right about in here. 2 a.m., the depth was 8.7. 4 a.m., 11.3. 6 a.m., 9.1, so we're back on the way down. So our peak here looked like at 11.3. 8 a.m., we were down to 3.8. 10 a.m., 0.1. And then at noon, we were back up to 1.2. So it doesn't look like we have a full cycle here, but we can see, our data is increasing. We hit our peak, and then we start coming back down. We bottom out. Our peak occurred at a depth of 11.3 feet. Our shallowest depth was at 0.1. So we want to model this to fit a trig function. Here's our basic trig function. Y equals some number a times the cosine of some quantity b times our time variable minus c. We close the parentheses and then plus d. And what we got to figure out here is what variables go in for a, b, c, and d that would make the cosine function fit the data that we have. We could also do this with the sine function. That would just be a shift to the left or the right. So let's start figuring out these variables one at a time. A, amplitude. That's just half the distance from a peak to a trough. Half from our max depth, our peak, 11.3. And we subtract our minimum depth, the bottom of the trough or the valley. And if we punch that into the calculator, we're going to get 5.6. So that's our amplitude. A equals 5.6. So we've already figured out what the A variable is, or stands for. The cosine function completes half of a cycle between the times at which the mins and maxes occur. So we can find the full period by just taking 2 times the time of the min depth and the time of the maximum depth subtracted. And if we bounce back here, we see our max occurred at 4 a.m., our min occurred at 10, so we want the difference between 10 and 4. Well, 10 minus 4 is 6, 2 times that is 12. So we know the period is equal to 12. And remember from a previous video, the period was equal to the usual 2 pi divided by b. The number in front of, in this case, it'd be the number in front of our t variable for time. Well, we know the period is 12. 12 equals 2 pi divided by b. If we multiply both sides by b, we'll get 12b equals 2 pi. And to solve for b, divide by 12. 2 pi divided by 12. And that 2/12 as a fraction can reduce down to 1/6, or in this, now it'll be pi over 6. So we figured out A, and we figured out B. Our left endpoint, remember our left endpoint will occur when this quantity in parentheses is set equal to 0. So we can find our left endpoint. We set, in this case, we're not using the variable x, but it's bt minus c equals 0. And we found b was pi over 6. So pi over 6 times t minus c equals 0. And I can add c to both sides. Pi over 6 times t equals c. And at this case, we know when our max occurred, when our first peak was. And that was 4 a.m. So for time, it's going to be the time is 4 a.m. So we plug in a 4 for time. Pi over 6 times 4 equals c. Well, that'll be 4 pi over 6. c equals 4 pi over 6. And that 4/6 will reduce down to 2/3 pi. So let's look at our equation now, and we can fill in what we've already figured out. We had y equals a times the cos of bt minus c plus d. Well, we figured out a was 5.6 cos. We solved for b was a 1/6 pi over 6 times t, and we just solved for c was 2/3 pi minus 2/3 pi. So now we just have to figure out this last letter d, and that's sort of like the average depth. Remember, our sine wave and cosine waves are wrapped around an axis, a center line. So somewhere through here is our center line. That's the average distance between the peak and the valley, the min and the max. So to find d, that's just the average depth, 1/2 of the high plus the low. 11.3 was our maximum depth, 0.1 was our low. If we punch that in the calculator, we get 5.7. So there's our trig function. Y equals 5.6 cos of the quantity, a 1/6 pi times the time, minus 2/3 pi, plus 5.7. And let me copy that. Now that we have a trig function that will help us predict, or that models our data very well, we can use that now to make predictions. If we look back on our original chart, we only had the depths at the even hours, 2, 4, 6, 8, 10. We can use this data to make predictions about the times that occur in between or at any time in the future. So if we want to figure out the depth at 9 a.m., we're just going to plug a 9 in for this t, and then we'll compute that on the calculator. And when we put that 9 in for t and compute that, our 9 a.m. depth is approximately 0.84 feet. 0.84. Let's see if that answer makes sense. At 9 a.m., 0.84 feet. So at 9 a.m., let's see here, in between here and here, we said we got a reading of 0.84. Does that make sense? After 8, 8 o'clock it was 3.8 feet, and then by 10 it went down, so we were decreasing, and our answer of 0.84 does fall within that range somewhere. So that answer is reasonable. For 3 p.m., we'd have to use military time. That would be 1,500 hours. So we would plug a 15 in for t, and we would get our 3 p.m. water depth would be approximately 10.57 feet. So about 10.5 feet at 3 o'clock. Yeah, and that's a little prediction in the future. We just went up to noon. If we continued that pattern up, maybe about, well, it'd have to be a little steeper than that. But at around 3 o'clock, 10.4 feet. We would be back up in here somewhere. So we're using that to make a little prediction about the future. Part C. Part C talked about a boat docking in the harbor. It needs at least 10 feet of water. What times could the boat dock? Graphing calculator makes this very easy. Here's our function that we graphed. You'd go into the y editor and enter your function, then graph that and the line y equals 10. So here is the water line 10 feet deep as the minimum. And we can see that here we're much too shallow. The boat could not dock. But there is some point in time when the water hits 10 feet. And that occurred at 14.7 o'clock. Now this is different because we're used to measuring time in minutes and seconds. This would be decimals. This would be a little after 2 o'clock. Accounting for the military time, that'd be 2.7 o'clock, or a little after 2:30, 2:40. Then the water level was above 10 feet for some point of time, and then the tide is going to start to go down, and we drop below 10 feet at about 17.3 o'clock, or 5 o'clock, 20 minutes after 5. For a single Hubble problem, here's a very similar problem. This deals with astronomy, and it talks about the illumination of the moon. The percentage y in decimal form of the moon's face that was illuminated on day X in the year 2009, where X and 1 represents January 1st, are shown in the table. Now these y values, when you see a 1, that's the percent illuminated. So 1.0 is 100% illumination, or that's a full moon. Where you get 0 illumination, that would be 0%, and that would be a new moon. And of course it's going to cycle back and forth between full moons and new moons. So here's some data. First, create a scatter plot, find a trig model that fits the data, add the graph from part B to the scatter plot. How well does the model actually fit the data? Figure out the period of the model, and then make an estimation, a prediction about the future for March 12th, 2009. That would be day 71 of the year. So graph the data on here and start working on a trig function. Pause the video, check back, and see if you got it right. Okay, first let's model that data. At 4, we had an illumination of 0.5. So we're right here on that line at a half. 11, day 11, we were at full moon. So day 11 is right in here, full moon. Next day would be 18, so that'd be 12, 14, 16, 18. At 18, we were back to a half moon. 20, 22, 24. At day 26, we were at a new moon, 0 illumination, so we're right here on the axes. Day 33, so this was 26, 28, 30, 32, 33 would be right in between, and we were at half illumination. That would be 34, 36, 38, 40. At day 40, we were back to full moon. So there is our plotted data. Again, if we connect the lines a little bit with a curve, we can see we have a sine or a cosine wave going on. We could model this data with either of them. It doesn't matter. So let me just write out the very generic form. Y equals A. We'll use cosine again. Cosine of the quantity B times X minus C, and then our plus D at the end. The first thing is amplitude. Amplitude is half the difference from the peak to the valley. So 1/2. Our peaks occurred at a height of 1. The lowest we ever went down into the valley was 0. So 1 minus 0 is 1, times a half is 1/2. So our A value is going to be 1/2. The period. The period is twice from a peak to a valley. So our peak occurred, this was at day 11, our valley at 26. The difference between 11 and 26. 26 minus 11. Well, 26 minus 11 is 15, times 2 is 30. And then we know that bx minus c equals 0. Oop, no, I'm thinking about the left end point there. So the period is 30, and we found the period by taking 2 pi, the unit circles radians, dividing it by b, the variable in front of x. And now we know that this is equal to our period, and we know the period is 30. So we would multiply both sides by b, get 30b equals 2 pi, and then divide by 30. b is going to equal 2 pi over 30, and we could reduce that down to pi over 15. So b equals pi over 15. And let's see here, we already got a half. We have b, pi over 15. Now we can get c, and that is going to be our left endpoint idea here. Bx minus c is equal to 0 is our left endpoint. Well, we found b was pi over 15. Pi over 15. And x is going to be the day of our first peak, our first hill. And that occurred at day 11. Day 11. And then we add c to both sides to get rid of this negative c. C is equal to pi over 15 times 11, or c equals 11 pi over 15. So we have a, b, we just found c. And the last thing we need is d. D, in the harbor example, it was the average depth, or 1/2 the high plus the low. So d is equal to 1/2 the high plus the low. Our high value occurred at 1, plus our low value occurred at 0. 1 plus 0 is 1, times 1/2 is 1/2. So d equals 1/2. And now we can rewrite this equation. I'll do it right above here in blue. Y equals 1/2 the cosine of pi over 15 times x minus 11 pi over 15 plus 1/2, where x is the day after January 1st. I think that was our setup. Where x equals 1 represents January 1st of the year. So there's our trig function that models our data. So we created a scatter plot, we found the trig model. If we did graph our data and the trig function that we come up with, they would not be perfect. I took the trig function that we found here that I outlined in blue, I put it into my TI-89, and for example, when I plugged in x is 4, I didn't get a perfect value of 0.5. I got 0.550 something. You know, it was pretty close. For 11, I did get 1.0 exactly. The 26 did turn out to be exactly 0, but the ones in between were slightly off, very minimal. The period of the model we found, the period was 30. And then part E, represent the percent illumination on March 12th. That's day 71 of the year. So what we could do is just run through this equation, plugging in a 71 for x. If you do that and punch that into your calculator, you're going to get a y value of equal 1. And remember, 1 is our percent illumination. That is a 100% or a full moon. So that gives you a little peek into how these trig functions can be used to model and make predictions about real-life phenomena that occur in a periodic nature.